Hi everyone, my name is Amanda Lee and I'm a doctoral student working with Dr. Kyle Hassenstab. We study chronic obstructive pulmonary disease, a progressive lung disease characterized by the destruction of small air sacs in the lung called alveoli, and chronic bronchitis. COPD is currently diagnosed using spirometry or lung function testing, which does not account for lung structure. Recent studies have shown that convolutional neural networks, a subset of imaging-based machine learning algorithms, can accurately predict COPD severity stage from CT images alone. Although accurate, imaging protocols within these studies require 2 lung CT acquisitions, one at full inspiration and one after normal expiration. Expiratory images are not clinically standard, and their acquisition increases patients' exposure to potentially harmful ionizing radiation. In this study, we sought to determine the added benefit of a second acquisition for CT-based COPD severity staging. We hypothesized that a single CT acquisition contains the majority of information necessary for imaging-based staging. To test this hypothesis, we sampled 7,823 inspiratory-expiratory lung CT image series from the COPD gene study cohort. We also deformably registered expiratory series to inspiratory series using a CNN-based deformable image registration algorithm. In addition, we used spirometry measurements and demographic information, such as sex, age, height, and weight. We trained 4 models, the first 2 models with either inspiratory or expiratory CT image series only. Then we trained a model using both the inspiratory and the expiratory series, and finally we added in the deformably registered series. The models were trained in a 2-stage process. First, the original image-only models were trained, and then we appended a multi-layer perceptron network to the final fully connected layer of the CNN to incorporate demographic information into the predictions as well. We predicted the following spirometry measurements: the forced expiratory volume in 1 second, or the FEV1, the ratio of the FEV1 to the forced vital capacity of the lungs, or the FEV1-FVC ratio, and the percent predicted FEV1. The last 2 measurements are used to stage COPD in clinic, which I'll discuss on the next slide. To stage COPD, the FEV1-FVC ratio is used to detect the disease, with ratios above 0.7, making up our gold stage 0 healthy control group. Then, FEV1 percent predicted is stratified into severity stages called gold stages, with gold stage 4 being the most severe. Here you can see the staging in action. We predicted the spirometry measurements and used these to estimate gold stage. In these plots, you can see that each point's true gold stage is shown by its location and its predicted gold stage is shown by the color of the point. These plots show that the CNNs preserve the ordinal behavior of the gold staging system, with the most CNN predicted classifications within 1 stage of ground truth. Here we show our gold stage prediction accuracy, our within 1 stage accuracy, and our binary stage accuracy, which represents the accuracy of predicting COPD versus non-COPD. Interestingly, the single CT series CNNs achieved comparable within 1 stage accuracy to the CNNs with additional CT series, and the model which used expiratory images as input outperformed the model which used the clinically standard inspiratory images. To verify the CNN's focus on the lungs, we extracted attention maps from each CNN. These maps are useful for visualizing the enhanced low-level and high-level imaging features important for prediction. Here, maps from each of the single image models are shown side by side, with the inspiratory model on the left and the expiratory model on the right. We found that the low-level maps indicate strong attention toward the high attenuation vascular structures, with secondary attention toward the lung parenchyma. We also note that the maps indicate attention toward gas outside of the body, as shown here. Finally, we found that the high-level maps mostly focus on areas within the lungs. Our results suggest that a single CT acquisition provides comparable performance to CNNs incorporating multiple CT series, and that expiratory acquisitions provide better performance than the inspiratory clinical standard. The diagnosis and staging of COPD using a single CT acquisition can reduce patients' exposure to ionizing radiation and improve accessibility to CT-based severity assessment while preserving performance. Finally, we plan to explore future directions for improving our current prediction accuracy. We used mean squared error as our loss function, which is sensitive to extreme values. To remedy this, we are incorporating a correlation-based loss function into our training pipeline, and we look forward to sharing the results of this adjustment at the ACSESS meeting in April. Thank you for your time, and I'll look forward to speaking with you there.